Hi, everyone. In class Monday, we started talking about, we talked about a lot of things. We talked about a new circuit element called an inductor, a coil, and a coil with a current going through it creates a magnetic field. But the magnetic field that it creates exists in the area spanned by the coil, which means creating that magnetic field induces an EMF in the coil that frankly works against the field we just tried to create. That response led us to define inductance. We developed a general equation for inductance in terms of the area of a loop, the number of turns per unit length, the number of turns, and the permeability of the space. We said that let me write that stuff. We said that the EMF induced in an inductor is related to the rate of change of current through the inductor and the inductance of the inductor. And just for clarity, we said L was an L. The inductance of a coil has to do with the permeability of the medium, number of turns, cross-sectional area, and the length of the coil. We said that we can store energy in the magnetic field according to the inductance and the current passing through it at any given time. Think of the inductance. The inductance is working against us, kind of like the potential difference that we set up across a capacitor as we move more and more and more charge. Use green for the capacitor. For parallel plates, we have that relationship. We said that the energy stored in an electric field have C delta V squared. And you can see the comparison here. As we move additional charge onto a capacitor plate, the potential difference that that creates makes it harder for us to move the next one, and then the next one, and then the next one. And as we move additional charge, we have to do more work each time. So we get this voltage squared dependence. How much energy can we store? It's related to the capacitance. Okay, so same story here. As we increase the current to increase the field, each time we do that, the inductance, the natural sort of self-response of the coil, works against us. So each time we change the current to change the field, we have to work against the natural response of the thing. So it's a very similar deal. We end up with the current squared, like we had the voltage squared. How much energy can we store? Well, it has to do with the inductance of the coil, which has to do with the coil's geometry, just like the capacitance has to do with the capacitor's geometry. We've also talked about a resistor. Which depends on its geometry as well. Use a lowercase l here. I don't want to confuse capital L with this capital L. They're not the same. So I'm going to use a lowercase here. The length of the wire or the element, the cross-sectional area, it also depends on its geometry. We can't store any energy in a resistor. The only thing we can do is dissipate. So I'm not going to put anything here. This top equation talks about the average EMF. The average, remember, EMF is potential difference. They're the same. That the potential difference that exists from one side to the other of a coil is related to how fast we're changing the current through it. We could write an equation like that for a resistor. In fact, we know what it is already. It's Ohm's law. We don't care about the rate of change of anything. What the current is, the potential difference, we say delta V, the potential difference across that resistor is according to Ohm's law. To get an equivalent statement here that relates the voltage across a capacitor to something about the capacitance to something about the current, we have to do a little bit of work. We already have it already. I mean, it's a very little bit of work. Check it out. Q C delta V. We're this close. Let's talk about the rate at which Q is changing. So let's talk about a delta Q, delta T. Let's just divide both sides by delta T. How much Q per time, and then the right side per time as well. We can do that as long as we divide both sides of the equation and delta T isn't 0. But delta Q over delta T, that's current. So we're talking about, it's a really similar really similar equation. Instead of asking about the rate of change of current, now we're asking about the rate of change of the potential difference across the capacitor, relating it to the capacitor. Now, since we're talking about inductors, we might be talking about AC current, and we might need to talk about the RMS voltage and current. It might be nice to have an equation like this, to just say, all right, the potential difference across the capacitor is this when this much current goes through it. And it might be nice to have a similar equation, that the potential difference across the inductor is equal to this when there's this much current across it, or what have you. So we reach a little further and we define reactance. Deriving these equations needs a little bit of calculus. We could do it. But let's just write them. So we're treating the inductor and the fact that it has a self-inductance, which tends to oppose putting additional current through it, kind of like a resistor. So what is the sort of resistance profile, call it reactance, of an inductor? We said in class Monday that it was given by, we defined it as omega L, where omega is related to the frequency of the alternating current, and L is the inductance. And the logic here, the more if the reactance increases, that we're gonna put that in an equation the potential difference across an inductor we can write as current times reactance instead of resistance. It's kind of like Ohm's law, but it's a little bit different. If we increase this by increasing omega, passing a given amplitude current, passing a given amplitude AC current through a resistor gets us a greater potential difference across the inductor. The inductor reacts more strongly. These are either amplitudes, that the amplitude of the voltage, because the voltage will vary sinusoidally, or the amplitude of the current. Either amplitudes or RMS. This is not an instantaneous function. I'm going to put RMS or peak. Either RMS or amplitudes, not at any given instant. We could make the same definition for a capacitor. Turns out to be 1 over omega c. Greater the capacitance, the less reactive, the less the capacitor gets to react when we try to pass current. In other words, if we increase this for a given current, we have to decrease the voltage response. Similarly, if we increase the frequency of the alternating current, we said in class one day that it's hard to rapidly alternate current. You don't build up any voltage. For a given amplitude and a given capacitance, the faster you alternate, the smaller delta T becomes. So the smaller delta V gets to be. And another way to say that is that the potential difference across a capacitor again we could define the reactance of a resistor, but there's no frequency dependence. We don't have to wait for the rate of change of anything. It doesn't matter what frequency we alternate the current. It's still Ohm's law. So the potential difference is still equal to IR, and that one is instantaneous. Whatever the current is, potential difference will be. It also works for RMS and peak, but it works for the instantaneous case as well. The case where things are changing. That's this first row. This is what we said in class. I just wanted to go through it again, kind of put a little bit of a nice finish on it, line it up in a table. It's nice that way. While we're here, I want to check a couple things. I want to make sure that the dimension of all these reactances is the same, because I'm about to compare them. If the unit of reactance is supposed to be ohms, does this actually have the unit of ohms? Does this? Let's find out. We'll come back to this. Omega. Wow. Omega is 2 pi f. F has the unit of things per second. Cycles per second. So this is 1 divided by 1 over seconds. Capacitance, which is farads. It's a 1. Now, a farad, hold on, C was Q over V, so this is a coulomb per volt. So a farad in the denominator means coulombs per volt. Now, a coulomb per second, that's an amp. And volts over amps, that's ohms. What about the inductor's reactance? Does it have the right units? This is going to take a little more thought because I'm not entirely sure what the units of inductance are. We had a slide that defined them as henries, but what's a henry? Two pi f is hertz, 1 over second. We can try to get the units for L from here, but I'd rather get them from here. We solve for L, volt cross multiplied by delta t, so we've got volt seconds divided by amps. Volt second divided by amps. Well, 1 over second, volts divided by amps. We just said that was ohms. Cool. Ew. These have the dimensions of resistance, so they should behave like resistance. Let me stop a segment here.